Hello everyone, my name is Xinyu Ma and I'm from Mid Sweden University. Today my topic is estimating harvestable energy in time-varying indoor light conditions. For wireless sensor networks, light is an energy source that can be harvested by photovoltaic cells. This picture shows a typical light energy harvesting system consists of a transducer, energy buffer, DC-DC converter, and load. The question is how to dimension a light energy harvesting system. For example, the question, what would be the solar panel size? And what would be the energy buffer storage capacity? In order to solve these questions, we need a power estimation method that can be used to estimate the available energy that can be harvested from the ambient environment. Before that, we need to get an idea of the ambient environment. For example, in the light conditions, what is the intensity and what is the spectrum? From the intensity and the spectrum point of view, we can see that the outdoor condition and the indoor condition are quite different. The intensity of an outdoor condition is typically hundreds thousands of lux, but for indoor condition, it's typically hundreds of lux. And the spectrum of an outdoor condition is the spectrum of sunlight. But for indoor conditions, if the artificial light change, the spectrum will also change. This picture has shown the spectra of artificial light sources and the sunlight at the same intensity. We can see that they distributed differently on the wavelength range. Actually, the real-world scenario is much more complex than this one because of the coexistence of sunlight and artificial lights. What are the influence factors for power estimation? If we measurement of ambient environment, what values we need to obtain from that environment is the question we want to consider before we doing the power estimation. We consider that both the intensity and the spectrum need to be taken into account. So our power estimation method is showing this way. This is the intensity and the spectrum values that we can collect it from the environment. By using them, we can classify the ambient environment into different light types and using the PV models accordingly to do the power estimation. This kind of spectral information can be provided by low-cost light sensors. For example, some lux sensor can be used to distinguish the visible and the infrared channels of the spectrum. And some RGB sensor can be used to distinguish the red, green, and blue color composition of the spectrum. This is our data acquisition device. We have embedded some ambient light sensors and RGB sensors on the surface around the PV panels. This device can be deployed to any light conditions to obtain data set of the spectral parameters. A PV model models the procedure that converting the intensity to power. The PV modeling for high illuminance outdoor conditions is later developed, but we need PV models for indoor low intensity. So we have proposed a 3D data-driven model based on the IV curves. This is an example spectral composition we measured from an indoor light conditions by our data acquisition device. And This different color showing the different channel of the red, green, and blue and infrared spectral composition. And all of this spectral and intensity information can be used as the input of our classifier. This color bar has shown the classification result. We can see that the light condition of the whole day is classified into different light types, such as sunlight, light, and fluorescent. If we have a look at the power curve, the black one is the measurement result, and the blue one is from our proposed power estimation method. The others are from the power estimation method that neglecting spectral information. We can see that during the day, this room is strongly illuminated by the sunlight, and the light condition is classified into sunlight. The selected sunlight model gave a power estimation result that most close to our measurement. During the night, with pure fluorescent light turned on, the classifier also determines the light condition to fluorescent. At the sunrise and sunset, the classifier suggests neither sunlight nor fluorescent, but determines the light source into light because it has a coexistence of sunlight and fluorescent. This figure has shown the energy estimation result for 24 hours for our 8 light conditions for both amorphous silicon solar panel and crystalline silicon solar panel. We can see that our spectrum and illuminance-based power estimation method has an error smaller than 6% for all of the light conditions. And for crystalline, the error is smaller than 9%. If we don't take the spectrum into consideration, the error will increase up to 60%. And for crystalline, it will going up to 50%. If you are interested in our raw data, you can find all of the 8 real-world light condition data set in this link. Now we can make some short conclusions. With limited spectral information, we have shown that the power estimation accuracy is improved. And this is enabled by light condition classifier and accurate PV models for low illuminance. Thank you for listening. If you have any questions, please feel free to ask.